Hello, JuliaCon. My name is Pete Vilter. I'm joined by my colleague Nathan Daly from Relational AI, and today we're going to tell you about the new memory allocation profiler we built with some help from the community that's coming out in Julia 1.8. So first, I'm going to talk about the motivation for building this tool. Why would you want to use it, and what does it do that other tools that already exist can't do? Then Nathan's going to give you a demo of using the tool to optimize a codebase with a performance issue. Then we're going to talk about future work and give some thank yous to the community. All right, so let's say we're in this situation. We're working on a module. In this case, it's a function which takes a two-dimensional array and serializes it to a CSV file. And we've written some code. Let's run it. And we find that the performance is not quite what we were hoping for. It takes almost a second to serialize my array, and allocates quite a lot of memory, and it spends over half of its time in garbage collection. So this doesn't seem quite right. My data is already in memory. Why would I need to allocate more memory just to serialize it to a file? So I need to investigate this. I need to fix this. What should I do? Well, something this small, I could just look at the code, and some of you may be able to spot this issue already. But in a large code base like the one we have at Relational AI, that's not going to work. We have too much code. We need a tool to really tell us where the problem areas are. So how can I do this? How can I know what part of my code is allocating all this memory? Well, I could take a CPU profile, but that's going to show me all the code that's running. It's not going to highlight the allocation sites. Also, it's not going to tell me the type that's being allocated, so I don't really have a good idea of what's being allocated. Also, I'm going to see the garbage collector in the CPU profile, but that can be triggered at almost any time, so it's going to be hard to to attribute that garbage collection time to the code that's actually allocating so that I can fix the allocations. There's also a mode called track allocation, which shows me line by line which lines of code we're allocating a lot. But it's missing call stacks. So if I see a line of code, for instance, in the Julia standard library that's allocating a lot of data, I don't really know what function from my code was calling into that function. So what do we need? Well, we need a tool that's going to give us types, call stacks, a nice visualization, and hopefully a familiar interface like the profile module we know and love. All right, that's what we built, and Nathan's going to give you a demo.
Thanks, Pete. So let's take a look at the profile. All right, so the API is very similar to the profiling API you might have seen before for the CPU profiler, except for all the functions now live under this Alex submodule. So we're going to clear the profile, and now we're going to start a new profile. So the API is just use @profile, but you can set a sample rate, which is very similar to the sample rate that the CPU profiler has. What it says is this controls what percentage of the allocations actually get sampled into the profile. So a sample rate of 0 or close to 0 means you sample very few of the allocations, and a sample rate of 1 means you sample all the allocations. The reason we let you control this is because profiling is very expensive, and so if your program allocates a lot, like millions or billions of allocations, having a high sample rate can really slow it down. So what I recommend is you first run with @time, and if you have only in the few tens of thousands of allocations, it can be okay to sample 100% of the allocations, but usually I would set a much smaller number. We're going to sample all the allocations here, and then we're going to visualize the profile we just took. So we're going to use pprof for this, which is a profile visualizer. And again, there's now an Alex submodule that we recently added to pprof, which lets you visualize allocation profiles. And we're also going to use this from C equals false parameter, which filters out internal Julia stack frames that are written in C because those can be distracting. Okay, so now we're in pprof. So pprof is a visualization tool from Google that's been wrapped into Julia, and I'm not going to explain it here because there's a lot to cover, but you can read about it online. The main thing to know is that there's a few different modes in pprof for visualizing a profile. This one that it defaults to is the graph view, which can be especially useful if you have a recursive program or a program where a few functions are very small but show up a whole bunch of times, and so when they're aggregated, you can actually see where the problem is. But I'm going to start by looking at the flame graph because that's what you're probably more familiar with if you've used other profiling tools. And so here's our serialize function that we were looking at. And this is a allocations profile. So every one of these allocations shows up in this profile aggregated together. And you can see that half the allocations, 20,000 of them, went through this string concatenation function. And the other half came over here through a stringify of an individual integer. And at the very bottom, you can see the actual allocations. So we allocated strings over here and strings and byte vectors over here. So this helps you figure out where your allocations came from. And it doesn't immediately surface the problem. Another view that you might look at, which can help, is to look at the number of bytes that were allocated in your program, not just the number of allocations themselves. And so you can only do this accurately if you captured 100% of the allocations like we did, because we only uniformly sample in the allocation space, not the byte space. But here you can immediately see when you switch over to bytes where the problem is, because 99.8% of all allocations went through string concatenation, 280 megabytes, whereas only half a megabyte was allocated over here from the other side. And so, okay, we know string concatenation is the problem, but we don't know why it's a problem. So another useful view in pprof is the source view, where you can actually see the source code and you can see the allocations in line. So this can be really useful. And so in this case, you can see that these lines were the lines that were directly responsible for all the allocations. And indeed, you can see it's doing string concatenation, and it's also doing the stringify here. So you might now see the bug. The bug is that string concatenation returns a new string every time it's concatenated. So building up a long string like this has a quadratic performance issue. If you want to concatenate 10 values together, you're first going to build one string, and then a string with the first 2 values, and then a string with the first 3 values. So to build a string with 10 values, you're going to have built 10 squared many allocations. So this is bad, and we want to fix it. Now we know where the problem is. We can switch over to the fast version of our code, which Pete has baked for us already. And in this fast version, rather than building up the intermediate strings, we're going to print the values directly onto the I/O buffer. So the I/O buffer can build up all the values as you go. You don't need to build up these intermediate strings and concatenate them together. All right, let's see if it's any better. So before we timed our slow version, we saw it had 300 megabytes of allocations. And if we now time the fast version, we'll see that it has just about 1 megabyte of allocations. So 300 times better and half as many allocations. Okay, so that's how you use the tool. Last, I wanted to cover the implementation. So this tool is implemented by instrumenting some Julia functions that do allocation to report out the size and the stack trace for every allocation. And when we could, we also report out the type being allocated. But unfortunately, these two orange functions don't have the type passed into them right now. So for those, we still report alloc unknown type. And so future work is to fix that, and then also to integrate with more visualization tools. And finally, we wanted to show the documentation is available online. It could still be improved, certainly, but we're working on that. And we wanted to say thank you to all these people who helped contribute to this project, including Tim and Elliot, who had PRs that we based this work off of, Valentine, Sasha, and Ian, who helped with this PR, and our coworkers, Nate, Nadia, Max, and Dean, who helped use the profiler and report issues. And you can find our code available here, and thank you so much for your attention.